Something big is coming, something so profound, it threatens to rewrite the very origin of the universe. For over a century, the Big Bang Theory stood as the cornerstone of cosmology, the grand explanation for how everything began. But today, new evidence from the James Webb Space Telescope has shaken that foundation to its core. In just its first year of observation, Webb has spotted over 30,000 ancient galaxies, and among them, one stands out. Astronomers call it the Big Wheel, a gigantic, perfectly formed spiral galaxy that existed less than 2 billion years after the Big Bang, long before anything like it was supposed to exist. According to every model we've trusted, galaxies that early should be small, chaotic, and misshapen, mere fragments of what would later merge into structured giants like the Milky Way. But the Big Wheel defies that story completely. Its light began traveling toward us 12 billion years ago, yet when Webb caught it, what appeared wasn't a cosmic infant. It was a fully mature galactic disk, spinning with the grace and symmetry of a modern superspiral. The numbers are staggering. The Big Wheel stretches 30,000 parsecs across, about 3 times wider than the Milky Way was at the same age. It holds billions of stars, and it rotates at speeds matching today's most stable galaxies. By every measure, it's a finished masterpiece, existing in an era where only chaos should rule. Astronomers ran the odds, the chance of finding a galaxy this massive and well-structured so soon after the Big Bang, less than 2%, and yet, there it is, clear, bright, undeniable. The discovery doesn't just bend the rules, it shatters them. If one Big Wheel exists, how many others are hidden in the cosmic dark? And what does their existence say about the very laws that built the universe? Webb's deeper surveys have made the mystery even worse. Across its ultra-deep fields, it's revealed a sky teeming with ancient galaxies, far more than any cosmological model predicted. Under the CDM lambda cold dark matter model, the reigning theory that combines dark matter, dark energy, and general relativity, such galaxies shouldn't exist in such numbers, brightness, or maturity. Simulations like illustrious TNG and Millennium predicted only a handful of massive galaxies in that young universe. Instead, Webb found thousands, each one glowing with hundreds of millions, even billions of stars, systems that should have taken eons to assemble. And it's not just quantity, it's efficiency. To burn this bright so soon, these galaxies must have turned their raw gas into stars at 2 to 3 times the maximum rate our physics allows. Normally, galaxies convert about 10 to 20% of their gas into stars. Webb's data demands efficiencies of 40, 50, even 60%, levels that border on the impossible. So, what's going on here? Have we misunderstood how galaxies form, or is something far deeper happening in the early universe? Astronomers like Michael Boylan-Colchin and Garth Illingworth now believe the problem is systemic. Not just one outlier, but an entire generation of massive, mature galaxies appearing billions of years too early. The models can't keep up with the data, and that means one of two things must be true. Either our simulations are missing something fundamental, or the universe itself isn't playing by the rules we thought it did. But the puzzle doesn't end there. Another shock is coming, one that could shake physics at its deepest level. Recent results from the Dark Energy Spectroscopic Instrument DESI have added fuel to the fire. By analyzing the light from 15 million galaxies and quasars, DESI built the largest 3D map of the universe ever created, a cosmic lattice stretching across billions of light years. Its measurements reveal something that shouldn't be possible. Dark energy, the mysterious force driving the universe's expansion, may not be constant. For decades, cosmologists believed dark energy had a fixed strength, a steady push encoded by the cosmological constant. But DESI's data suggests otherwise. It hints that dark energy strength, represented by the parameter W, might be changing over time, drifting from about -1.4 in the distant past to around -0.7 today, with statistical confidence strong enough to grab the community's attention. If true, that means the very force pulling galaxies apart is weakening. The cosmic engine itself is slowing down, a direct challenge to Einstein's idea of a static cosmological constant. That single clue could rewrite everything, from the universe's birth to its ultimate fate. And yet, the contradictions keep multiplying. Even the universe's expansion rate refuses to agree with itself. Measurements from the Planck satellite suggest a value of 67 kilometers per second per megaparsec, while local galaxy observations give 73, a split that refuses to close. No matter how precise the instruments get, something fundamental is missing. And the more we look into the cosmos, the more it seems like the universe is hiding its true story. This isn't just a minor disagreement. It's an 8% difference that refuses to vanish. A cosmic standoff between the ways of measuring the universe itself. For years, astronomers tried to close the gap between the local and early universe expansion rates. But now, with the James Webb Space Telescope joining the debate, the tension has only deepened. Adam Rees, Nobel laureate and leader of the SHOES team, spent decades refining how we measure cosmic distances, using Cepheid stars as mile markers to gauge how fast space is stretching near us. With Webb's razor-sharp infrared vision, his team recalibrated a third of Hubble's entire sample. The result? A local Hubble constant of 73.5 with an error margin under 2%, nearly identical to Hubble's previous numbers, but now too precise to dismiss as error. Every cross-check agrees. Every galaxy and supernova whispers the same story. The nearby universe is expanding faster than the early universe predicts. Meanwhile, data from the Planck satellite, reading the faint afterglow of the Big Bang, the cosmic microwave background, insists on a slower value of 67.4. The two numbers refuse to meet in the middle. They are carved into the data itself, as if the universe is keeping a secret for cosmologists. This is more than just math. It's a crisis of understanding, a sign that something fundamental is missing from the standard model of cosmology. Either the equations we've trusted for decades are incomplete, or the universe behaves differently than we've ever imagined. But then, a new idea rises from the edge of theory, David Wiltshire's timescape cosmology. It suggests that the universe's patchwork of galaxy clusters and cosmic voids doesn't just shape matter, it shapes time itself. In this model, time doesn't tick at the same rate everywhere. Inside dense clusters like our Milky Way, gravity's pull is strong. It slows time, ever so slightly. But in the vast, near-empty voids between galaxies, clocks tick faster. The difference sounds small, but over billions of years, it adds up. Wiltshire's calculations show that clocks inside galaxies could lag by as much as 35% compared to those drifting in the emptiness of intergalactic space. That means if the universe has aged 13.8 billion years in a void, only about 9 billion might have passed for us, here, inside a galaxy's gravitational grip. When scientists reanalyze the pantheon plus supernova data without assuming a uniform cosmic clock, the results stun them. The data actually favor the timescape model, with strong statistical backing, over the standard cosmological constant. In this vision, the universe's apparent acceleration isn't driven by dark energy at all. It's an illusion born from the way time stretches and slows across the cosmic web. We may be watching the universe's expansion through a distorted clock, one that ticks slower where we live. And just as that revelation sinks in, a new anomaly emerges. Astronomers studying galaxies at extreme distances, billions of light years away, notice something strange. The spins of these ancient galaxies aren't balanced. Roughly 2/3 rotate clockwise, while only a third spin the other way. That's a 66-33 split, far beyond what random chance would predict, confirmed at a 3-point for Sigma's significance level. It's not confined to one corner of the sky. It's everywhere. It's as if the universe itself remembers a direction, a cosmic fingerprint printed at birth. Some theorists believe this imbalance might be a clue, evidence that the universe was born inside a rotating black hole. Physicists like Nikodem Poplovsky propose that if our cosmos emerged from the other side of such a black hole, that primordial spin could have given the entire universe a preferred axis, a direction that everything from galaxies to particles still faintly obey. If true, every spiral galaxy becomes a fossil, a swirling memory of the universe's first rotation, an echo of the spin that birthed it all. For now, these ideas remain on the edge of science, bold, controversial, and unconfirmed, but the evidence keeps growing. Every new dataset from the James Webb Telescope, every supernova light curve, every galactic spin measured, pushes us closer to a truth stranger than fiction. Maybe the Big Bang wasn't the beginning we thought. Maybe the universe is older, layered, and shaped by time itself. Or maybe, just maybe, it began with a twist. One thing is certain, the deeper we look, the less the cosmos obeys our expectations. The universe is not silent. It's whispering. And what it's saying could rewrite everything we think we know about where we came from.